That's right, closely packed and not closely packed. Remember when we discussed diffusion rates? So creep is very much a diffusion controlled process. So if you have a crystal structure which is closely packed and has low diffusion rate, you end up with better creep properties. And by having some noticeable amount of beta phase in the material, you might actually deteriorate the creep properties of such a material. And that's why creep properties are mentioned here, because you don't have, well, apart from a very, very tiny amount of beta phase to mop up nitrogen, you don't really have any beta phase here. And so that can be beneficial. Strengthening is done through thermomechanical processing. What does that mean? What, when I write something like this, this is actually a very general statement. What is actually behind that? When I say strengthening by thermomechanical processing, what do I mean by that?
Forging.
Sorry?
Forging.
Yeah, but why? Why does forging strengthen the material? Yeah.
Grain size, so you get whole patch strengthening.
Yeah, and that's exactly right. But can you just briefly explain why the forging does that? Well, there's also work hardening. That's right. You might get just work hardening and strengthen the material by that. But you said, sorry, what did you say?
A whole patch relationship.
So what? How do you reduce the grain size?
So when you heat material up with hit it crystallizing, I'm not sure how to say
yes.
it.
No, and that's why that's why I just want to discuss it now. So in principle, you're right. I mean, so you put work into your material, right? You increase the dislocation density, and that itself strengthens the material. So you might just leave it there. And just to, I often find that, it's all a bit abstract maybe for you, but when you think of a stress-strain curve, and you've all seen stress-strain curves by now, I presume. You have this elastic regime and then you get plasticity, right? That's what you get. And work hardening means that you deform your material and let's say you stop here. So you unload. If you load this material again, what happens? Yes, well the yield stress is now here, isn't it? You just go back up. So I'm just trying to, make sure that you really understand what is work hardening. It's really just, you can demonstrate work hardening in a simple tensile test or compression test where you follow the stress strain curve, you unload and you reload. That is your work hardening, right? And that is purely based on increasing dislocation density in your material. Now, if you do that, you go here, you unload. Let's say you do this all at room temperature, or you might have to do that at elevated temperature because the material, you can't deform the material easily at room temperature. So that's thermomechanical processing then. And you heat up the material now. Instead of reloading it, you heat it up. What might happen? Recovery or recrystallization. And really what you want to achieve is recrystallization, like you said. And the recrystallization, what happens during recrystallization? What is it actually? What does it mean?
Rearrange themselves and support sort of sub-grain grain boundaries, which that then becomes your new grains.
yes, you essentially the dislocations, they rearrange themselves and form nuclei for new grains. It's a way of reducing the energy state in your material. And because you elevate the material to a higher temperature, the dislocations are now mobile enough to rearrange themselves. One thing I really encourage you to do, all of you, is talk to your peers about these things when you prepare for an exam. All right? You see how, by talking about it, you learn so much. Unfortunately, we don't do oral exams anymore. When I was a student, I only had oral exams. So I always had to learn how to talk about it. And I think that's the only way why I was able to learn it in the first place. So, I encourage you to talk to your peers, to your friends about it, and explain to each other these simple things. You can so easily go through the slides for revision and say, oh yes, strengthening by thermomechanical forcing. But what does it mean? All right. So you form new grains, and therefore because they nucleate, they're small and then they start to grow. So that's a fundamental way of refining the microstructure, and that's the way you can strengthen alpha titanium alloys. And either you just keep the work in the material, or you do the heat treatment to recrystallize it. And of course, the problem is when you have to hot roll or hot forge the material, that it can be quite tricky to actually retain the stored energy without getting too much recovery. Because when you get too much recovery, you don't store the energy, and you might struggle to recrystallize the material. So another point here is, and I think there's one example here, if these materials are intended to be used at very low temperatures, so for cryogenic applications. Cryogenic application means you use it at temperatures well below 0 degrees. What is done is that you have an alloy variant which is very low in interstitial. So this EILI means that it's very low in interstitial. So very low in oxygen, nitrogen, all these elements which are go interstitial into the lattice. Because they strengthen the material, but they also make it, especially at low temperature, reduce the ductility of the material. So, and these alloys are quite difficult to process, and so they are not that common these days. And then we get to the alpha plus beta titanium alloys. So these are now the dual phase titanium alloys. You want to, John? Oh yeah. So they, I've already mentioned it. Well, they essentially have beta phase now also at room temperature, and not just in tiny pockets to mop up the hydrogen, but you really have noticeable or detectable beta phase in that alloy at room temperature. And because it's a dual phase structure, they are actually inherently stronger than single phase alloys. So they're stronger than CP titanium, and typically stronger also than alpha titanium alloys. And there's the grain refinement can be quite effective because it's of the two phases. They are widely used by the aerospace sector, but also by the offshore industry. So essentially, whenever you need higher strength, you use those. And as I've already, I think, mentioned a few times, and you should be aware of that, titanium 6 aluminum 4 vanadium is the workhorse of titanium alloys. So that if there's one alloy I would like you to remember, it's this one. And they need to, because these alloys, they are too strong to be processed at room temperature. You can't roll them or anything at room temperature. So they are thermomechanically processed, and they're actually processed at relatively high temperatures. And so what that actually means is they are processed when you have relatively high amounts of beta phase. And you can see that here, but I actually have another graph here, schematic. And this is really quite important for you to understand. So it's a bit like a binary phase diagram, not properly, because essentially what I've done here is I start not with titanium, but I say, okay, I start with titanium 6 aluminum, right? And I add beta stabilizers along here, so vanadium. Okay, temperature like we have in phase diagrams. And so what you find is that once you have a certain amount of certain amount of vanadium in that alloy, so it's really what we're talking about here is titanium 6 aluminum X amount vanadium, and the X goes up. And eventually we have enough vanadium in the material that at room temperature we now start to see beta phase. Right? That's the principle. But I would like to point out to you that, of course, okay, so you go up in temperature here, and you eventually reach a two-phase regime, alpha plus beta. And you now, because this is not pure titanium anymore, in pure titanium, you would go straight from alpha to beta, right? As you go in pure elements, you go straight from one phase to the other. In alloys, you have a two-phase regime in it here. So you have a small window of two phases here. Of course, as you increase now the beta amount of beta stabilizers, so vanadium, that temperature at which you start to see the beta phase comes down, right? And eventually it's down to room temperature. So it's really quite simple. If you add a lot of vanadium, you eventually end up with pure beta phase, even at room temperature. And you can see that the more vanadium you add to that system, the more beta phase you end up having at room temperature. So you can just apply the lever rule and work that out in principle. What is important though is that if you now assume that this is here where we have our titanium 6 aluminum 4 vanadium, and we are in the two-phase regime, as we heat up, we start changing the volume fraction of alpha and beta phase. Okay, and that's something I want you to understand. It's not very noticeable up to maybe temperatures of 700 dVc, but further up you start to see it clearly. So it's the line is a bit vertical, it's fairly vertical initially, and then it starts bending over, and that means really you start to get more and more beta phase at fairly high temperatures. And so when you think about thermomechanical processing now, what I want you to realize is that depending on the temperature at which you forge or roll the material, you actually have different fractions of alpha and beta phase. And that has a very pronounced effect on the microstructure you generate and the texture you generate, crystallographic texture you generate in your material. You can also even thermomechanically process the material up here in the single phase regime. And that's also done at certain stages. And then you can see here that here there's a dashed line, and this is kind of a line indicating the martensite start temperature, or it's essentially if you're on the left hand side of that dashed line down here, you can, when you cool your material or you quench your material, you get this phase transformation, the martensite phase transformation. You cannot retain a lot of beta phase during quenching. It just transforms martensitically. If you are on the right hand side of that dashed line here, if you now quench the material, you will actually just freeze the high temperature microstructure. So you just retain your beta phase. It's not stable, it's a metastable condition, so if you anneal it afterwards, it will transform. But during quenching, it will not form this kind of fine lath structure which I've shown you here, but it will just retain the beta phase. It's a bit like retaining austenite, which can also happen in steel. So if you, for instance, have high levels of carbon in steel, you probably learned that you have retained austenite in it. And here, the way it works is if you have too much beta phase, beta stabilizes, and you get that as well. And that's, you might want that. And of course, I mentioned earlier near beta titanium alloys, and they actually exploit that. So we will discuss that later. Okay. Near alpha titanium alloys. So I've already mentioned that briefly. So they have less beta stabilizers than, for example, titanium 6-4. There's an example here. This is a high pressure compressor disc from I think that's a Rolls-Royce engine, and it's made of an alloy called Ti-Metal 834, and it's just a near alpha titanium alloy. It has improved high temperature capability due to lower volume fraction of beta phase. The why we've already discussed earlier, right? So, you reduce the amount of phase which has high diffusion rates, and you improve the high temperature capability of that material, particularly creep. It is quite a difficult material to process in general. It's not easy to machine and weld. They also tend to have additions of silicon, and silicon is added here to provide additional solid solution strengthening. It seems to actually pin dislocations and quite effectively. And they also form silicite, and you can see here some TM images of a relatively fine microstructure. In this case, it's actually also Ti-Metal 834, and you can see these black precipitates here. These are actually silicides, and they tend to sit on the grain boundaries. So they strengthen the grain boundaries, and that's, it's believed to have a further contribution to improving the creep strength. Although I have to say that I don't think people have fully agreed on if it's the silicides which really help a lot, or the silicon which is left in solution, which seems to really also help in terms of pinning the dislocation and maybe reducing diffusional climb of dislocations. I don't think researchers ever really got to the bottom of that. But overall, silicon has a very good positive effect at high temperatures. Maximum temperature capability of these alloys is around 600 degrees C. And so applications are medium pressure compressor part and aeration. You will not find, as far as I'm aware, you will not find this type of alloy anywhere else than in a medium pressure compressor part of an aero engine. You will not find it anywhere else. These type of alloys were purely developed for the air engine sectors. And the driver was really to reduce the amount of nickel in the engine. Why would you like to remove the amount of nickel in the engine?
Reduce weight.
Reduce weight, yeah. Exactly. Titanium is much lighter than nickel. So you want to reduce weight. And that was really the driver. So, I don't know if I can quickly go all the way to the beginning where I had this one slide here. You see, you have titanium at the front here, and then you cross over to nickel. And the temperature in that engine essentially goes up, goes up, goes up. Highest somewhere here, and then falls down again near the outlet. So you somewhere need to swap over from titanium to nickel, because nickel will give you higher temperature capability than titanium. Now if you have a titanium alloy which has much better high temperature capability, you can essentially push back the nickel a bit further and reduce the weight. That was the thought process here when these alloys were developed. Nowadays, and so you still find them in quite a lot of engines, but as far as I know, in the latest engines, like the Trent 900, 1000, XWB Rolls-Royce engines, so with the ones which drive the A380, the 787 Dreamliner, and the A350. I don't believe, actually, I don't know, do you know that there's no A34 anymore in these engines? You don't know?
No, I don't.
Okay. And the reason is that, I'm pretty sure that's the case. So the issue is that in order to, how do you improve the efficiency of an air engine? Apart from reducing weight.
Improve the temperature.
Yeah, you increase the temperature in the engine. And that's what is happening. And so the temperature has gone up so much that actually the red has actually pushed back further forward. So there's actually now more nickel in these engines than there was before, and slightly less titanium. So the titanium is not so much going back here anymore. So just to put this all a little bit into perspective. But there's still a lot of this alloy in the air because there are quite a few engines which use it. And of course these engines are also still built. I mean, it's not that they just stopped building the old engines. Okay, one thing I would like to point out here. Why do you have any idea why we can't push titanium alloys to higher temperatures? You might actually say that. I think if it could be an issue. I think you could probably go a bit higher before you see that.
Because maybe above this temperature, the titanium oxide is not protecting anymore.
Very good, very good. Titanium and zirconium have actually very poor oxidation properties at high temperatures. So oxidation is actually a big problem. So that's a limit. There's another limit, and that is that titanium is actually not burn resistant at very high temperatures. So it can ignite. And because you have rotating parts, so let's say you might also use 834, one of these near alpha titanium alloys, for the blades, where you have the highest temperatures. So the temperature actually rises from the center to the outer part, not just along the engines, but also radially all the time. And if you now have the blades rubbing against the casing, at very high temperatures, titanium can ignite. And having fire in an engine is not a good idea. Really not. So that's the other reason why at some stage all this development of very high temperature titanium alloys stopped, because it was recognized you just can't go beyond 600 degrees C. So here are some examples. Again, please don't think you need to learn these alloys. It's just, what I always say is have a look at this table and try to understand like what the alloying elements do. And here, for instance, you can nicely see how this alloy 811 has a very high beta transverse, because you have a lot of aluminium here and very little beta stabilizer. So here's the, it's actually here it's called IMI 834. It used to be the company used to be called IMI, was a British company, was bought by the Americans by Ti-Metal. It's now called Ti-Metal 834. They're still, the UK base still exists. They're still in Birmingham, and they still produce a lot of titanium. It's a very interesting company. And here you can see it's quite a complex alloy. So you can see the silicon, which I mentioned. There's actually a tiny amount of carbon. I don't really know what the purpose of this. A tiny amount of niobium, which is a beta stabilizer. Molybdenum. Now, actually, I haven't really pointed that out. That the modern near alpha titanium alloys, they've replaced vanadium with molybdenum. And the reason for this is molybdenum is a much more slowly diffusing element than vanadium. So molybdenum is a slow diffusing element. It's a beta stabilizer, but it's really slow and has very slow diffusion rates. And for high temperature application, that's very beneficial. But molybdenum is, actually it's the molybdenum which makes it quite tricky to process the material as well. Then you have zirconium, and tin, and they are neutral elements. They're really added for solid solution strengthening. And then you have the aluminium. So the 6242 and 834, they are very common alloys. In fact, 6242 remains a very common alloy even in modern engines. But yeah, and you can see here, so you can draw the line here essentially. Everything above this line here, so everything from 6242 onwards, upwards, is considered a near alpha titanium alloy. Everything below is is more kind of an alpha plus beta titanium alloy. And you can also see that even 6.4 has a low interstitial variant. So you can see the oxygen drops from 0.2 to 1.3, or even lower actually. I think these numbers are a bit older. I think generally the oxygen levels are much lower these days in both types. Okay. And then I think that's, yeah. So the last class of titanium alloy is what I've mentioned also already earlier, are the near beta titanium alloys. And one famous application for them is that actually some of the A380s, I don't believe all of them have that, have a landing gear made from a near beta titanium alloy. And as you probably know, I guess you all know what the A380 looks like. Yeah, it's a double-decker aeroplane by Airbus. Really always looks